All right. Okay, so welcome to this last lecture. So I'm going to continue with acceleration. I want to show you Nesterov's momentum and the proof of it, and then we're going to move to more recent topics. I will try to do a full proof of stochastic variance reduction, and then give you some pointers to what are currently exciting directions. So right now we're still in lecture 4, which was acceleration. And this is the third topic in that lecture, which is Nesterov's accelerated gradient descent. Okay, and this was developed in 1983. All right, so as you saw before with Nemirovsky's acceleration, the key was to reuse the previous gradient, right? When you have smoothness, it's suboptimal to have those memoryless algorithms that just remember where you are, use the current gradient, and move according to this. Because with smoothness, you want to exploit, the whole regularity of the vector field of gradients. And the breakthrough in Nesterov's method is that his key insight is the only thing you need to know about the past is your momentum. Okay, so the key breakthrough is that all that matters about the past, is the momentum. Okay, so what is the momentum? The momentum is just where you're coming from. Okay, so I will call dt is going to be some number gamma t, which is like a step size, gamma t times xt minus 1. Okay, this is the momentum term. You were at some point, xt minus 1. You move to this point xt. Here you have a certain gradient, and you have a certain momentum. Okay, so maybe this is the momentum, and this is a gradient, or negative gradient. Okay, so the intuition for this momentum term comes from physics. So Polyak in the 60s proposed the following algorithm. So Polyak's heavy ball method. His intuition was, of basically just a ball rolling, in a potential where you have both the gradient of the slope plus the momentum. Okay, if you had some energy coming in, this is going to add to the slope. So what he suggested was the following algorithm: xt plus 1. It's equal to xt, and let me denote gt. That will be, maybe I don't write it for the moment, or maybe I write it, yeah. So xt plus dt. Okay, so you remember xt plus, the notation from the previous hour? Xt plus is just x plus, is just x minus 1 over beta grad f of x. It's just a constant step size gradient descent, where the constant is 1 over the smoothness, and we know the appropriate improvement for such a step. Okay, so you do a step, and you add the momentum. What is Nesterov's accelerated gradient descent? It's just a smarter version of this. Okay, so this method does not accelerate. All right, you can show it on very simple example of quadratic functions. Okay, it does not achieve what it's trying to do. What Nesterov proposed is the following. It's xt plus dt plus. Okay, so you first take the momentum, and then you compute the gradient. You do this kind of look-ahead gradient. You compute the momentum, and then you compute the gradient at the point you arrive with the momentum, and you step from there. It's clearly stronger. Okay? Or I don't know clearly. It is clearly stronger because, you're going to end up there. So you want to compute the gradient information at that point. It's smarter than computing it here. If you already know that moving in the direction dt is a good idea, just do it and get the information over there. Okay? So this is Nesterov's momentum, really very beautiful, and we're just going to analyze it now. And I will show to you that it achieves the same rate as Nemirovsky's acceleration. Okay, note in particular that Nemirovsky acceleration was doing this plane search Here there is nothing like that. It's really very elegant. Okay, so the analysis is famously magical, and sadly, it will be extremely simple, maybe 2 boards at most, but it's still going to be slightly magical. Okay? I mean, you can motivate it by, again, looking at all the analysis that I didn't do, the formal analysis of smooth gradient descent and all of that, and trying to trick the parameters there. I'm not going to do that. I'm just going to show you the proof, and let's hope you can just follow, and that will be it for acceleration. Okay, so let's see, what do I want to do? So denote, let me introduce some notation. GT is minus 1 over beta, the gradient of f at xt plus dt. Okay, by the way, I still need to clarify what is gamma t, right? I didn't make this precise yet. Just like in the lambda t sequence, I didn't make the lambda t sequence clear. Okay, so denote gt to be minus 1 over beta grad f of xt. So xt plus 1 is nothing but xt plus dt plus gt. Okay, and I'm going to now write 2 inequalities that we have written many times, which is an inequality on the suboptimality gap at time t plus 1, and an inequality on the improvement from time t plus 1 to time t. Okay, so I'm going to write 2 inequalities. One is going to be delta t minus delta t plus 1, and the other one is going to be delta t plus 1. And maybe I write it like this. Let me just make sure I don't mess this up, because otherwise it's going to be a nightmare. Yeah, that's how I want it. All right, so what is this? This is f of xt plus dt plus minus f of xt. And this one is f of xt plus dt plus minus f of x star. Okay, this is the 2 things that I want to bound. So what am I going to use? I'm first going to use the inequalities that I know on the improvement of a step of gradient descent. Okay, so what do I know about the step of gradient descent? I know that this is smaller than f of xt plus dt. And the improvement that I get is exactly 1 over 2 beta, the norm of the gradient. Okay, so in terms of the gt, it gives me minus beta, so let's see if I get it correctly. Maybe I just write it like this. Minus 1 over 2 beta, norm of grad f at xt plus dt squared minus f of xt. And now I'm just going to use the convexity. Okay, so this is smoothness. Now I'm going to use convexity on this one. And what do I get? I get grad f of xt plus dt, inner product with xt plus dt minus xt, which is dt. Okay, minus 1 over 2 beta, norm of grad f at xt plus dt. L2 norm squared. Okay, so now let me write this just in terms of my gt. So what is this? This is minus beta gt dot dt minus, and here I want, if I get a gt, I want beta. Beta over 2 norm of gt squared. Okay, I really didn't do much so far. This is just an upper bound on the improvement that I get from one step to the next in function value. Now let me upper bound my distance to opt. My distance to opt, so I can do the same thing, right? The only difference is this. Instead of dt, I'm going to get xt plus dt minus x star. So I immediately get that this is bounded by minus beta gt dot xt plus dt minus x star minus beta over 2 norm of gt squared. Okay, so far no magic. I'm just writing out the inequalities that I get with the momentum using convexity and with the gradient step using smoothness. And in fact, the only magical step is what I'm going to do now, which is not magic at all. I'm just going to take a combination of those two inequalities and see what I get. Eventually, all of those proofs, many of those proofs, you want eventually to get a telescopic sum. Remember, with Nemirovsky's acceleration, what we were computing was the sum of the lambda s delta s. Okay? And what we were showing is some kind of self-bounding property. Often what you want to upper bound, each term individually is by something which is summable, so that you get a telescopic sum when you sum them. Okay? So this is all we're doing right now. I'm just going to combine those two inequalities to get something of this form, and then massage the right-hand side so that I get a telescopic sum. That's all which is going to happen. So let's call this 1 and 2. So the plan is combine 1 and 2 to get some left-hand side smaller than right-hand side with left-hand side of the form, say, sum of WS, some weighted combination of the delta S, and right-hand side, telescopic sum. Okay, so if we had done the formal analysis of smooth gradient descent, very simply you get quantities like that. So it's pretty natural to try, in this more general Nester's acceleration to, again, trying to mimic those proofs. And I'm going to smartly take some lambda t minus 1 times 1 plus lambda t times 2. So for some lambda t, I'm going to look at lambda t minus 1 times 2, times 1, sorry, plus lambda t times 2. Okay, I'm just taking some combination of this, and with these parameters, there are going to be lots of nice cancellations. All right, so let's do it. What is this? Okay, so I have a minus beta g. Okay, so first of all, I have minus beta over 2 gt squared. It's in the two inequalities, so I get lambda t times this. So I get minus beta over 2 lambda t times the norm of gt squared. That's one term that I get. Now for the other one, I have minus beta gt inner product with two different things. One of them is dt, and the other one is xt plus dt minus x star. So when I lambda t minus 1, this one, plus lambda t that one, what am I going to get? In front of the dt, I'm just going to get, what is going on? Probably, sorry. Do I want plus 1 times? Lambda t minus, of course. Yeah, I just want plus 1 times here to have the nice cancellation. Sorry about that. Plus 1 times 2. Yeah, so sorry. So then I get lambda t minus 1 plus 1. That was correct. Okay, so now in terms of the dt, I get lambda t minus 1 times the dt plus 1 times the dt. So I get lambda t times the dt, and I get once the rest. Okay, so again, minus beta gt inner product with lambda t dt plus xt minus x star. Okay, and what is this? This is like the left and the, let's say. So this is upper bound, this is lower bounded by lambda t minus 1 times delta t plus 1 minus delta t plus delta t plus 1. Okay, so this is the inequality we have right now. Okay, and all I'm going to do now, that's the inequality. Now I'm going to choose the various parameters to get my telescopic sum on the right-hand side. And on the left-hand side, I will identify that I have some weighted combination of the delta S. Okay, so far so good? All right, so how am I going to get a telescopic sum over there? I'm going to use, again, my favorite identity, which is what in this case? So I have some norm of A squared plus 2A dot B. So what is this in terms of something telescoping? It's the norm of A plus B squared minus the norm of B squared. Right? I have some norm squared plus of some A plus A times B. So I'm going to write it like that. Okay? It's not rocket science. Right? So right-hand side, it's minus beta over 2. So I put my beta over 2 in front of everything. And then what do I get? And maybe I put my lambda t also in front of everything. Yeah, I'm going to put a lambda t also in front of everything, like a 1 over lambda t. So then what do I get? I will write A is lambda t gt, and B, okay, lambda t gt, and B is lambda t dt plus xt minus x star. Right? And just say lambda t norm of gt squared. It's 1 over lambda t is the norm of lambda t gt. And here I put a lambda t also. All right, so what do I get? I get the norm of A plus B. Okay, let's just write it. So the norm of A plus B, it's xt minus x star plus lambda t dt plus lambda t gt L2 norm squared minus the norm of B squared, the norm of xt minus x star plus lambda t dt L2 norm squared. Okay, I'm not super happy because it doesn't look like, you know, a ut plus 1 minus ut. So now I need to work to make that happen. So the hope, so goal, or slash hope, let's see if it works, is to say that xt plus lambda t dt plus lambda t gt, I hope this would be really great if this was xt plus 1 plus lambda t plus 1 dt plus 1. Okay, I'm saying if this term, you know, without the minus x star was the same one as this one with a t plus 1, then I get my telescopic sum and I'm in business. Okay? So let's try to do that. You can see that if I messed up somewhere, I'm going to be in trouble with this type of proof. But so tell me if I'm making a mistake somewhere. All right, so what is this term? This is xt plus dt plus gt plus lambda t plus 1, gamma t plus 1, x t plus 1 minus xt. Okay, and xt plus 1 minus xt, this is dt plus lambda t plus gt. Okay, so it's getting a bit better because I have only xt, dt's, and gt's on the left-hand side and the right-hand side. So hopefully I can start to canceling some stuff. Okay, first, okay, the xt cancels. That's one thing that cancels. What else cancels? Not that much. So what do I get? I get that this is equivalent to, I get lambda t dt plus gt. I wish this was equal to, I get dt plus gt on the right-hand side. Times what? Times 1 plus lambda t plus 1 gamma t plus 1. 1 plus lambda t plus 1 gamma t plus 1. And now I'm happy. I can choose gamma t plus 1. So this tells me to choose gamma t plus 1. So choose gamma t plus 1 such that lambda t is equal to 1 plus lambda t plus 1 gamma t plus 1. I haven't chosen lambda t yet, so you know, we're getting there. Okay, so now on the right-hand side, we get a telescopic sum. Okay, if I call this, so, maybe even though I shouldn't use colors, I have to use it because otherwise it's too many things. So if I write ut, which is the norm of xt plus lambda t dt minus x star squared, we just proved that this right-hand side is equal to minus beta over 2 lambda t, ut plus 1 minus ut. Okay, so when I will rescale by lambda t, I get something telescoping. Okay, so what do I get exactly? If I go over there, what was the left-hand side? The left-hand side was, so what is this? I get lambda t times delta t plus 1 minus lambda t minus 1 times delta t. Okay, so if I multiply by lambda t on both sides, what do I get? So we have, I multiply by lambda t on both sides, we have lambda t squared delta t plus 1 minus minus lambda t squared minus lambda t times delta t. This is smaller than minus beta over 2 ut plus 1 minus ut. And now I still have the choice of lambda t. So what am I going to choose? I'm going to choose lambda t so that I get also a telescopic sum on the left-hand side. Okay. So now choose lambda t such that lambda t squared minus lambda t is equal to lambda t minus 1. Okay, so now you get lambda t squared delta t plus 1 minus lambda t minus 1 squared delta t is smaller than minus beta over 2 ut plus 1, and maybe I remove the minus, ut minus ut plus 1.
Don't you want lambda t minus 1 squared there?
I absolutely do, yes. Thank you very much. Yep, exactly. Note, this is exactly the same thing as what we had for Nemirovsky's acceleration. The lambda t sequence is the same one. Yeah. Okay, so now I can just sum those things. Okay, I will get some remainder terms I don't want to worry about. But basically actually, yeah, if you just define lambda 0 to be 0, this will immediately imply lambda t squared times delta t plus 1 is smaller than beta over 2 u0 or u1. U1. U1 is what? It's just the distance to the optimum at the start. It's just always, our distance to the optimum at the beginning, squared. So again, I just need to estimate lambda t squared. But I just told you it's the same equation as Nemirovsky's acceleration. So this is solved. You can just solve the formula. But this is going to be lambda t is of order of t. Right? Because again, t squared minus t minus 1 squared, it's like t. Okay, that's the derivative of x squared. So what I will get is t squared times delta t plus 1 is more than beta distance to the origin over 2. So in the end, I get, okay, I can just write it, delta t plus 1 is smaller up to some constant, beta, x1 minus x star squared over t squared. Okay, because lambda t is t, so lambda t squared is t squared. Okay, I will let you judge whether this was magic or not, but this is the proof of Neserov's acceleration. Yeah, please.
Is there a continuous time analog of this that maybe give us some physical intuition?
Yeah, so I don't think continuous time is the right question to ask for acceleration. because the whole point, was smoothness is about how well can you discretize the continuous time process. So it's more about, the natural continuous time process is gradient flow, and then what I'm saying is with, smoothness, there are smart ways to discretize it. So there are papers by very good people actually, that try to derive continuous time versions of Nesterov acceleration, and you can do it. This is a gradient flow with some, other terms that depends on the acceleration of the PDE. But I don't know exactly what they say. I mean, they suggest a certain phenomenon, and then you can try to, change the algorithm to fit this phenomenon that they discover with the continuous time analysis. But it's not going to give new proofs, I think. Does that answer your question? I mean, it's both a reasonable and not so reasonable question. But very reasonable people have asked it, so, anyway, maybe I shouldn't have said that. Okay, any other question on this? So there are other ways to derive accelerations. There are like many papers now. I think I suggested one of them for the papers to present next week, a much more geometric interpretation, but it's not a geometric interpretation of momentum. It's a geometric algorithm that gives you these rates. Okay, is there any more question on acceleration? So by the way, this where I showed you, okay, one more comment. I showed you this 1 over t squared rate, okay, so 1 over square root epsilon, but I said you can also get this square root kappa log 1 over epsilon. So you can, you can either do Nemirovsky's acceleration or Nestorov's acceleration. There are variants of those proofs that give you the square root kappa. There are also very general reductions. So basically, anything which is a 1 over square root epsilon, that will be a square root kappa. You can work out those reductions. I can give you references if you're interested in this. That's not the hard part. Okay. All right. So then we move to the last chapter. Which is going to be about variance reduction. Okay. So lecture 5. Some variance reduction techniques. So this is a more recent line of research of the last decade, roughly. And it goes like this. So let's do first the finite sum problem. Okay, which is one of the problem of machine learning. So you want to solve a problem like this. 1 over m, the sum for I equals 1 to m of fi of x. Let's say this is your f of x. And let's say you're doing logistic regression or least squares. This is a smooth, each one of them is smooth. It's a smooth loss function. And maybe you have added regularization, maybe not. But it is also strongly convex overall. That's going to be our assumption. So fi is beta smooth. And f is alpha strongly convex. Okay, so if all the fi's are beta smooth, then the entire f is beta smooth. Okay, it's just a stronger assumption. So we know right now a couple of algorithms to do that. We know stochastic gradient descent. So stochastic gradient descent, remember, it's just xt plus 1. It's equal to xt minus eta gradient of fit of xt. Okay, so you take a random example, a random function here, and you take the gradient with respect to that one. Okay, and you just sample them at random. And as we have discussed, this is like the multipass SGD, so it's going to converge to the minimum of this guy, okay, of the training error. If I were doing a single pass, if I never revisit an example, then I can invert say that I converge to the minimum of the generalization error. Just remind you this discussion. Now gradient descent is xt plus 1 is equal to xt minus eta over m, the sum for I equals 1 to m of the gradient of fi of xt. Okay, so gradient descent does a full pass through the data at every time step. Okay, and I can also do AGD, accelerated gradient descent. So what do I know about those convergence rates? So SGD, it's a strongly convex problem. I didn't show it, but the strongly convex proof that I did was robust to noise. So this has rate 1 over alpha epsilon. And this one has rate kappa log 1 over epsilon. Or square root kappa, okay, if you do acceleration. Now, note, very importantly, these two numbers are not exactly measuring the same thing. This is the number of data points that you touch, right? The gradient computation touches one data point. So to put them on the same scale, I need to do m times here, m times kappa. Okay, these are the number of data operations. Okay? And note they are not directly comparable. If I want to have a small epsilon, then this is going to be better because it doesn't have the m in it. Okay, think again, beta is some constant. So kappa is really like 1 over alpha. Okay, so this is better for small epsilon, for large epsilon. But for very high accuracy, this is much better. Okay, is there some middle ground? And also, just intuitively, full gradient descent really doesn't make sense for this type of problem because it doesn't move until it has seen all examples. Clearly, you should be able to move a bit before. Okay, so there should exist something in between those two algorithms. And there is, and it was one of the big breakthroughs in optimization of the last decade. So I will tell you that. I mean, big breakthrough in the sense that it's also a very practical method. You can really use it. Okay. All right, so we're clear on what we're trying to do. We're trying to bridge the gap between this low accuracy, but it gets to move immediately type of method, and very high accuracy, but slower, like, it takes more time to move. Okay. So the key idea, okay, what's the problem? First of all, what's the problem of, say, SGD? It's that you have a small learning rate. Right? You have no hope to get to a high accuracy regime, a log 1 over epsilon, if you're taking those very tiny steps. You will just never get there. You have to take big steps. But if you take big step with SGD, why do you need small learning rate? It's because of the variance. Okay, you have too much variance in those estimators. You see, even when you get close to the optimum, even when you get a predictor which is the best, it might still have very big gradients, because on some examples, maybe it's very bad. Okay, so this algorithm does not have this auto-tuning of when you get close to the optimum, the gradient itself is getting small. And that's what stops us from taking a big learning rate. But the idea is, because anyway we're going to have to touch m example, is that from time to time, you can recompute a full gradient and use this full gradient to recenter your estimator. Okay, so the key idea is, from time to time, compute a full gradient. I mean, typically, certainly, every m time step, I can afford to recompute a full gradient. Now, what is the gradient that I want to do? Now, GT, my estimator, would be the gradient at a random point of xt. And now I'm going to center using the gradient compute the full gradient at some point y. So I do this of y plus grad f of y. Okay, so this is the key idea, this equation. So my stochastic gradient, I take a random example, I compute the gradient there, but I use my centering sequence. I have some point y, which is going to move much more slowly than xt. And when y moves, I recompute the full gradient. Now, notice in expectation, this is correct, because the expectation of this guy is exactly grad f of y. So those two things cancel each other. But now you see that I win, because if I get close to the optimum, this guy should be small. But if I'm close to the optimum, maybe xt and y are also close to each other, and then I can invoke smoothness, and this is also small. So this has some hope of having this self-tuning of learning rate. Okay. So the hope is that the expectation of the norm of gt squared gets smaller when close to the optimum. Okay, and I claim that if we have this property, I'm not going to show very succinctly, that just doing SGD but with those stochastic gradients will improve dramatically the convergence rate. Okay, so maybe I make some claim and theorem. So the theorem that we're going to prove is that the following algorithm is good. So let me just think what I want to do. During an epoch, which is of length t of order of kappa. Okay, so an epoch is going to be kappa of length, condition number of lengths. When my epoch finishes, I'm going to compute a full gradient and recenter things. Okay, so during an epoch, say again?
T is usually the letter we denote for the entire run.
I know, but it's going to be useful. Like the total running time is just going to be this capital T times log 1 over epsilon. I'm really going to show that in one epoch, you shrink the suboptimality gap by a constant. It's going to be, yeah, it's not a mistake to put it. But I understand what you're saying also. Okay, so during an epoch of that length, do the following. So let x1 be y, and I will have to explain what is y. And for any little t from 1 up to capital T, I'm just going to run my stochastic gradient descent like this. So xt plus 1 is going to be xt minus eta gt. Okay? Once this ends, what do? I put in the new y, I put the average, 1 over t, sum for t equals 1 to capital T of the xt, and recompute grad f of y. Okay, so I have an epoch. During an epoch, I have some centering point, which is not going to move at all during that epoch. I'm going to use this centering point to reduce the gradient of my noisy oracle, to reduce the variance of my noisy oracle. What do? I do SGD, but with this smart step. Once I have finished my epoch, I just average all the points that I've visited, and I move to the next epoch. Okay? And so the theorem is that f of new y minus f of x star is smaller than 0.9 times f of the old y minus f of x star. And this is with a large learning rate. That's the whole point. With eta, which is, say, 1 over 10 beta. That's what we're going to prove next 10 minutes. So this algorithm has a name. It's called SVRG, for Stochastic Variance Reduced Gradient Descent. Okay, so this is called SVRG. And now you see we can add one more here. So SVRG, what it does, you see I need to do log 1 over epsilon step to get epsilon accuracy of these things. And an epoch, how many gradient calculations do I need to do? I have kappa steps, and when I'm finished, I have m computations. So SVRG is m plus kappa log 1 over epsilon. Okay, which is much better than this m times kappa. Okay, gradient descent was doing m times kappa, and this is doing m plus kappa. Now you might ask, what about acceleration? Here I got a square root kappa. Okay, so you can do an accelerated SVRG. We're not going to do that. So accelerated SVRG, what it gives you, it's m plus square root m kappa times log 1 over epsilon. Okay, and these ideas are used, for real. Just like the momentum is also used for real. Okay. We're good with the statement? So the only state, I just need to worry about one epoch and to show this. Okay, so let's do the proof. So I'm going to use, we know exactly how to analyze those type of iterative methods. We've done it now multiple times. I can just write the sum of the inner product of gt with xt minus x star, and I can decompose it into a range term and a variance term. So let me just do that for you. So f nu y minus f of x star. This is by convexity bounded by 1 over t, the sum for t equals 1 to capital T of f of xt minus f of x star. And let me put expectations, very important. Okay, let me put an expectation here and an expectation here. So note that the expectation of gt is grad f of xt. So this is smaller than 1 over t, the expectation of the sum by convexity of gt inner product with xt minus x star. Right? This is just my new error is upper bounded by this. But my algorithm is exactly gradient descent on those gt. So again, we have done this calculation several times. This is upper bounded by your distance at the beginning. You start with x1, which is y. So you start with y minus x star squared over 2 eta t plus eta over 2 t, the sum for t equals 1 to capital T of the norm of gt squared. Okay, range term, like forgetting of the initial condition, the like gradient flow term, and the discretization term. Okay, so now I'm going to use strong convexity. Is there any question on this? Oh, it's clear? Okay, so now I'm just going to use the strong convexity to bound the range term by the gap in function value. And I'm going to use the definition of the variance reduced gradient to bound the variance term. Okay, so by strong convexity, we have that the norm, so we have alpha over 2 norm of y minus x star squared. This is a lower bound on f of y minus f of x star. Right, just because you go, that's the definition of the strong convexity, you go quadratically from any point plus the tangent, but the tangent at the optimum is flat, so you just get the quadratic term. Okay, so what do we get? We get that this term, so let's call it the range and the variance term. So what we get is that the range is bounded by what? Okay, so I get, I put a 2 over alpha, the 2 cancel. I get the gap, f of y minus f of x star, over 2 eta t times alpha. I just get eta t alpha. Okay, which is, remember, eta is like constant over beta, and t is constant times kappa, which is beta over alpha. Okay, so this is some constant times f of y minus f of x star, like 0.01. Okay, so the range term is just a very tiny fraction of the suboptimality gap, which is great. I mean, this was the old gap, and now we have 0.001 times the new gap. Okay, so now I just need to worry about the variance term. Is it clear, this? It's just the choice of the parameter. Step size is 1 over the smoothness. T is condition number, so, 1 over the smoothness, we exactly get T over kappa. Is there a question? Something is not clear. I don't see what's not clear, so you need to help me out. All right, let me continue then. So the variance term, that's the difficult one. The variance is the question is what is the expectation of the norm of gt squared? Okay, and here I need to somehow formalize this intuition that I had where I was saying that when you get this sentence, I need to formalize this hope that the variance of this thing should get small when we get close to the optimum. Okay, and I'm going to formalize this with the following lemma. So here is the lemma. The expectation of the norm of grad fi of x minus grad fi of y, L2 norm squared. Okay, so this looks like the type of variance terms that we will make appear. And here I really want at the optimum. I really want to say when x is going to get close to the optimum, in some sense, this should be small. And here the expectation is over y I sampled from 1 to m, uniformly at random. I'm going to show to you that this is bounded by 2 beta times the suboptimality gap. Okay, so I will do this proof. But before I do this proof, let me show how to end the calculation assuming this lemma. So assuming this lemma, what do we have? So this variance term, I get 2 things. I get it's bounded, I'm just going to use triangle inequality to bound that term plus that one, and I'm going to plug in the grad f of x star. So I get, this is bounded by 2 times the expectation of the norm of grad fi t of xt minus grad fi t of x star, L2 norm squared, plus grad fi t y minus grad f y minus grad fit x star squared and parentheses. Okay, so here I didn't do much. I just plug in, the gradient at the data point of the optimum. Now, notice that this is a variance term, and this is the expectation. Okay, and the expectation, so this is a variance, and the variance is smaller than the second moment. So this thing, in expectation, it's smaller than if I remove this term. So this is smaller than grad fit of y minus grad fit of x star, L2 norm squared. Okay, this is, again, just the expectation of the norm of x minus mu, where mu is the mean of x, is smaller than the expectation of the norm of x squared. Okay, I can just remove the mean when I do the variance calculation. So now I get two terms which look exactly like my lemma. Okay, so let me finish. So this will be the proof of the lemma. But now with this, what do we get? We get that the expectation with the lemma, we get that the expectation of the norm of gt squared, this is bounded by 2 times. Okay, I have a 2 and a 2, I get a 4. I get 4 beta times f of xt minus f of x star plus f of y minus f of x star. Okay, and the variance term is what? The variance term is eta over t times the sum of those things. So the variance term, variance, is now upper bounded by what? So I get 4 beta eta, and then I get 1 over t, I get the average of the gaps of f of xt minus f of x star, plus f of y minus f of x star. And now I claim I'm done, because 4 beta eta, this is a tiny constant. So what I get is that my variance is bounded by, again, a tiny constant times the suboptimality gap, plus a tiny constant times what I was trying to bound from the beginning. Here. This is what I was trying to bound from the beginning. So I can put this little term on the left-hand side. So if I put everything together from the variance is bounded by this and the range is bounded by that, I will exactly get that. Okay? So the variance satisfies exactly what we wanted. So all I need to do is to prove this lemma to you. Is there a question on the structure of this?
Y, the old y?
Yeah, this is the old y, yes.
So how are we?
Yeah, so we start with, we want to prove that the new y is better than the old y. The new y is bounded by this. Now, instead of bounding the new y, I'm going to bound that guy. So that guy, I just showed it's bounded by 0.01 times the old one, plus, maybe another 0.01 times the old one, plus 0.01 times what I'm actually trying to bound. So when I put it on the other side, I just prove that 0.99 times this is bounded by 0.02 times that, which is good. And 0.02 over 0.99 is smaller than 0.9 by quite a bit. All right, so all I need to show is this guy. And this is really, I want to emphasize, this is a key intuition. Okay, this lemma, it's going to be extremely simple, but this is a key intuition, this is a key formalization of the fact that when we're getting closer to opt, this thing is just moving less. Okay, because when y is getting close to opt, you just have the cancellations here between the gradient at it and, you see, here it's the gradient at it and the gradient at it. Okay. So the proof of this is like this. Let gi of x to be the following function. It's fi of x minus fi of x star minus grad fi of x star inner product with x minus x star. Okay, so I just look at the function on the ith data point. And this is the Bregman divergence term for those of you who know what this is. But it's just the difference between the value at x and the value at the linear approximation at the optimum. So this is non-negative by convexity. Now what do we have? So we know that a step of gradient descent on this smooth function improves by 1/2 beta norm of the gradient of gi of x. Okay, if I do a step of gradient descent on this function at that point, I will improve by that much. But I can only improve by gi of x. Why is that? Because gi of x star, gi of like gi star is 0. Okay, the optimum of this function is 0 just because at x star it's 0. Okay, so on this function, if I do a step of gradient descent, the maximum gain that I get is gi, and gradient descent gets that gain. So that gain is upper bounded by this. Okay, so this implies that gi of x is lower bounded by 1/2 beta norm of the gradient of gi of x. And there is a square. But now if you take the expectation of this inequality, it's exactly what I claimed. Okay, the expectation of gi, it's exactly f of x minus f of x star. It's exactly the suboptimality gap. And the expectation of the gradient of gi, the gradient of gi is just grad fi at x minus grad fi at x star. So this is exactly that term. Right, it's a cute proof of this fact. Okay, so this was just like a little piece of a growing literature on variance reduction techniques, trying to leverage the fact that we know more about the stochastic, like we can have smart stochastic gradients. Okay, so now let me just give you a list of some other topics that I could have covered with many more hours. So of course the list is going to be biased towards what I know and love. So going further. So we already talked this morning about like smooth plus non-smooth. Okay, so that is trying to decompose a function into a smooth part that we know how to optimize very well, and a non-smooth annoying part which is slowing us down, but that we understand and that we can use in the algorithm differently. Another simple thing in variance reduction is Minibatch. So Minibatch, SGD. It's instead of computing the gradient with respect to a single example, right? I had those two things. SGD is compute the gradient with respect to a single example, and gradient descent is compute with respect to the whole data set. You can compute with respect to a batch, right? So this is xt plus 1 is equal to xt minus eta over b times the sum over some batch of the grad fi of x. Okay, you just sample a random batch of size b. The point is, why can you improve? You can improve because the variance of this thing is going down. Okay, and what can you prove? You can prove that SGD on smooth. So note that on smooth functions, we know that we cannot beat 1 over epsilon squared, because the very first lower bound that I did yesterday was that 1 over square root t is the best you can do even on a linear function. This is as smooth as it gets. But what you can show is something like this: sigma over root t plus beta over t. So you can prove that the variance term goes down like 1 over square root t. So if there was no variance, you would get the beta over t. And on the other end, if it's very smooth, you just get the sigma over root t. Okay, so you get the best of both worlds. That's just SGD on a smooth function. And as an exercise, you can analyze what this rate, which we didn't prove, but it's not too hard to prove, implies for mini-batching. And you will see that you can get up to B, the size of the batch, which is square root M. So you can get this quadratic reduction, and it's not going to hurt your convergence rate. You will get the same thing as SGD. Okay? So mini-batching does not hurt because of this on smooth functions. So this opens up the entire literature of parallel optimization. So here you see we have focused on mostly on this very iterative method where you compute a gradient, you look at the answer, you move to the next one. But you can imagine that you could have multiple processors, and each of them can compute a gradient, and then you gather all of these observations, and you decide on what to do next. This topic is extremely interesting and very highly non-trivial. I will leave it at that. Another thing which I find interesting is the meeting of Kevin's class and this class, which is bandit convex optimization. So you've seen bandit linear optimization, and it's very natural to look at bandit convex optimization. This you can also do. You can do something like SGD on a convolved function. This will not give you the 1 over square root t rate. You have to work harder to get the 1 over square root t rate. Let's see, what else do I want to say? One entire class of algorithms that we did not touch is inter-upon methods. So inter-upon methods, they are roughly in the vein of the cutting plane method. They are kind of improvement of cutting plane. So this is how to handle complicated constraints, complicated K. Let's see, what else did I want to say? Prox method. Right. So let me finish with two other things. So I proved lower bounds on these linear functions, but in fact for least squares, you can still do something better. Okay, least squares is not a bad linear function. It has curvature in a certain ways, and you can do constant step size least squares. So what does that mean? That just means no 1 over alpha in the bound. And it sounds very technical, like constant step size, least squares, no 1 over alpha on the bound. This is extremely relevant. Remember, this 1 over alpha is exactly this phenomenon. If you have a small subpopulation in your big data set, it's going to slow down your progress if you want to nail down that subpopulation too. Because you have to have a learning rate that juggles between going slowly on those guys and rapidly on the rest. So it's pretty non-trivial to show this, but you can show it. And the last one that I didn't touch on at all is this mirror descent business, which is the observation that what we have been talking about for the last 5 hours doesn't make sense at all. So this equation, as somebody noticed this morning, does not make sense. Those things do not live in the same space. Okay, just very naively, this would be, say, a column vector, and this is a row vector. Okay, so you cannot add them like this. So what mirror descent is saying is that it's trying to take the high road and to say, okay, this is, very abstractly, this lives in your Banach space B, and this lives in the dual space. So what I need to do if I want to make this operation rigorous, I need to first map this to the dual space. How do I map it to the dual space? I can use a gradient of some other functional that is defined beforehand. So if I have this algorithm called, let's say, phi mirror descent, what I'm going to do is that I'm going to do grad phi of x minus grad f of x, and then apply the grad phi inverse, which is the Fenchel dual. So this opens up an entire different class of algorithm where now you measure smoothness. What's the point of this Banach business is that now you can talk about smoothness in L1, for instance. Okay, you don't have to have a Hilbert space anymore. But this is a different course. All right, is there any question? Yeah?
So if you do mini batches, and you do this gradient update, then could you improve on this theorem, right? Is it how we reduce the variance better?
Yeah.
How we would modify it.
Yes, it's not clear indeed. So I'm not sure how mini-batching would affect SVRG exactly. It's a good question. I don't know the answer. I mean, we can think about it. We can figure it out. Yeah?
The trivial one. What does the P stand for in that field?
Say again?
What does the P stand for in the acronym?
Interior point methods. And it's closely related to mirror descent in the sense that these are just two different discretization of, instead of gradient flow, it's Riemannian gradient flow. So instead of moving with respect to the Euclidean metric, you have some other Riemannian metric and you're moving according to that metric, which is an extremely natural class of flows.
So in the past 2 lectures, maybe 3, we did not care so much about the convex set K constraint.
Yes.
So is it because we can always do projections and...
No. It's because it gets messy. But you're welcome to go read Nesterov and figure it out. Yeah, I mean, it's just less pretty. But yeah, it's not just projection and everything works. But you can do it. Actually, in my monograph, I do also a bit of it. Yeah. All right, thanks.